Mathematics in the Modern World, Chapter 2. Topic: Elementary Mathematical Logic. Logic is the basis of all mathematical statements and arguments. Its basic rules are essential to understand mathematical statements like there exists an integer n such that n squared is equal to n. If x is an integer, then x plus 1 is also an integer. For all real number x, with x less than 0, x squared is greater than 0. Some applications of logic are in artificial intelligence, system specification, computer science, and many more. So let's start with the basic foundation of logic, the proposition. A proposition is a declarative sentence that is either true or false, but not both. The truth or falsity of a statement is called its truth value. Letters are commonly used to denote propositional variables such as P, Q, R, and S. Example: which of the following is a proposition? Number 1. The sun is the center of the solar system. This is a declarative sentence and we know that it is true. So this is a proposition. Second, kindly give me some sushi. Obviously, this is not a declarative, so not a proposition. What is the title of your favorite song? It's a question, therefore, not a proposition. Kobe Bryant is a tall person. It is a declarative, but there is a question if it's true or false, so this is not a proposition. Let's go back with the fourth. Kobe Bryant is a tall person. Why is this statement not a proposition? Yes, it is true that he is tall, but maybe for those who are shorter than him, so it is true. But for some who is taller than him, he is not tall. So this statement is true and false at the same time. So that makes this statement not a proposition because it cannot be both true and false. Statements like this are what we call a paradox, a declarative sentence which could neither be true nor false, or is both true or false. Types of proposition. A proposition is called simple if it contains only one idea. A proposition is called compound if it is composed of at least two simple propositions joined by logical connectives. Logical connectives are and, or, if, then, if, and only if. Example: the sun is the center of the solar system. Heart Evangelista is the wife of Senator Chis Escudero. President Duterte is the 16th president, while Vice President Robredo is either the 12th or the 14th Vice President of the Republic of the Philippines. If the books will arrive on Thursday, they will be distributed to the students on Friday. So, statements 1 and 2 are simple, while 3 and 4 are compound propositions. Basic logical operators. So we have negation, conjunction, disjunction, conditional, and biconditional, along with their meaning, symbolic form, and how you read them. Not P, P and Q, P or Q, if P, then Q, P if and only if Q. Let's start with negations. This logical operator states the exact opposite of a given statement. P, the sum of two odd numbers is even. So the negation would be the sum of two odd numbers is not even. Next, Q. It is sunny today. So the not Q would be it is not sunny today. There are only two possible truth value of P. It can only be either true or false. If P is true, then its negation is false. If P is false, then the negation would be true. Conjunction. We observe the connectives and, but, moreover, while, in short, and. Example, if you have P statement, 25 is a perfect square number, and you have q, 5 is one of the square roots of 25, then p and q, 25 is a perfect square number, while 5 is one of its square roots. Next, p, it is sunny today. Q, I need to go to work. So p and q, it is sunny today and I need to go to work. So we have here the truth table of a conjunction. If you notice, we have 4 rows because we need to take all the possible combination of the truth value of p and q. Both true, true, p is true, and q is false, or false if p and q is true, or they're both false. So you have 4 possible combinations. For the truth value of a conjunction, if both are true, then the conjunction is true. If true false, then the conjunction is false. If false true, then the conjunction is false. If false false, then the conjunction is false. If you notice, the only time our conjunction is true if they are both true. Next, disjunction. We observe the words or, unless, either or, etc. Or in short, or. Example, P, Mary will buy her clothes at the mall. Q, Mary will go to church on Sunday. So P or Q, either Mary will buy her clothes at the mall or she will go to church on Sunday. So there is the or there. Next, P, it is sunny today. Q, I need to go to work. So it is sunny today or I need to go to work. And here we have the truth table for the disjunction. The same combinations of the truth value of P and Q. If you notice, the only time the disjunction is false is when both are false. So, if at least one of them is true, then the disjunction is true. Conditional. We observe the words if then, only if, or implies, provided that, given that, etc. In a conditional statement, we say that P is a sufficient condition for Q, while Q is a necessary condition for P. P is called the antecedent of the implication, and Q is called the consequent of the implication. Example, the curfew is effective today, and the Q is the police officers will arrest lawbreakers. If the curfew is effective today, then the police officers will arrest lawbreakers. Another example, P, n is a negative integer. Q, n squared is a positive integer. If n is a negative integer, then n squared is a positive integer. In an implication, it means that if P is true, then Q is also true. However, an implication is directional. Example, if Q is true, it does not necessarily follow that P is also true. Let's look at the truth table of a conditional. If they are both true, then it is true. If P is true and Q is false, it is false. Why this is false? Because of this. It means that if P is true, Q must be true. That's why the conditional is false. The third one, if P is false and Q is true, it is true because of this. That if Q is true, it does not necessarily follow that P is also true. So pwede siya false. That's why the statement is still true. And when they are both false, then it is true. So you only have to take note of this one. Now, once your P is true and your Q is false, that's the only time that your conditional statement is false. By conditional, We observe the words if and only if, is a necessary and sufficient condition, etc. But usually if and only if. Example, I will graduate on time. Q, I will pass all the subjects this semester. So, I will graduate on time if and only if I will pass all the subjects this semester. Another one. The tournament will take place tomorrow. The weather is good. So, the tournament will take place tomorrow if and only if the weather is good. If the biconditional is true, we say that P and Q are logically equivalent. That is, they will be true under exactly the same circumstances. So if you look at the truth table, if P and Q are true, it is true. True and false, false. If false, true, it's false. If they are both false, it is true. P and Q should have the same truth value for the biconditional to become true. So true, true, it will give out the true. If they are both false, then the biconditional is also true. So you take note of this too. Let's translate each of the following statements into its symbolic form. Upon announcement of public storm warning signal number 3, classes in all levels should be suspended and children should stay inside strong buildings. So if we analyze this, we have connectives upon and then the statements is somewhat divided into 3 parts. So the first statement, public storm warning signal number 3 is announced. Then we also have classes in all levels are suspended. Then we also have children should stay inside strong buildings. Now, looking back, we have the upon that would give us a conditional statement. And then we also have the and, which give us the conjunction. So combining the P, Q, and R, we have P, then, so I cannot separate Q and R, so I will use parentheses, Q, and it is a conjunction, R. Next, 2 lines A and B are parallel if and only if they are coplanar and they do not intersect. So we have if and only if. Then we also have the and here, and we also have the not. Okay, so we also have here 3 statements. Start with P. 2 lines A and B are parallel. Lines A and B are coplanar. And lines A and B intersect. So if I'm going to write the symbol, I have here if and only if, so that would give me the biconditional na symbol. I have the and, so I also have conjunction. There is the not here, so I might negate statement R. So that would give me P if and only if. I have Q, and of course I'm going to negate the R. Truth tables of compound propositions. So this will be the summary of all the truth table from negation to biconditional. So a truth table is a table showing all possible truth values of a particular compound propositions. So we have here the summary, we have here the negation, the conjunction, the disjunction, the conditional, the biconditional. Construct the truth tables of the given compound proposition. we have P and not P. Since we only have one variable, which is P, so we only have two possible truth value, which is true and false. So we find the not P. So true, it will become false. From false, then it will become true. And then I'm going to find the conjunction of P and not P. If you recall, for conjunction, the only time the statement is true if they are both true. So true, false, 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 true is false. If all truth value of your compound statement are all false, then we call this one a contradiction. Let's have this compound proposition. If P then Q, or if Q then P. In this case, we have two variables, P and Q. Then we have four possible combination of their truth values. So we have true, true, false, false, true, false, true, false. So both true when one is false and if they are both false. Next, we need to find the conditional statement P then Q. Then we also need the Q then P. And then we combine the two. So let's start with the conditional if P then Q. So for conditional, you have to remember the only time that it will become false is when you have a true first statement, then it will give out a false consequent. So true, true, it's true. True and false, it's false. False, true, it's true. And if they are both false, true. Next, if Q, then P. So this time, the only time it will become false is when your Q is true and your P is false. So true, then this time it's true, false, and then we are going to look at these two columns. Okay, we're going to combine these two. Okay, so or for this junction, the only time it will become false is when they are both false. So true, true, it's true. False or true is true. True or false is also true. And true or true is also true. When all your truth value are all true, call this one a tautology. Next, we have P and not Q, then R. In here, we have three variables, P, Q, and R. So that would give us 8 possible combinations of their truth values. It's basically 2 times 2 times 2. That's why we have 8. So we need to find P, Q, and R combinations. And then we also need not Q. Then we combine it with P and not Q. And then we have the conditional P and not Q, then R. So to find the combinations of P, Q, R, you can follow this pattern. True, 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 false, 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 false. True, true, false, false. True, true, false, false. And then true, false, true, false, true, false, true, false, false. Alright, so next for the not Q, so we only have to look at this column. So false, false, true, true, false, false, true, true. And then we're going to combine P, this column, and the not Q. So we're only going to look at these two column. And it is a conjunction. So it should be both true to make the statement true. So true, false, false. True, false, false. True, true is true. True, true is true. False, false is false. False, false, false. False, true is false. And false, true is also false. And then we have conditional statement. This column and this column. So we're going to combine these two. You have to remember, for conditional statements, the only time it will become false is when you have a true then false. So false true is true. False false is true. True true is true. True then false, then it's false. False true is true. False false is true. False true is true. False false is true. So if you have this kind of compound proposition, which is a mix of true and false, then we call this one a contingency. So tautology, contradiction, and contingency. So a contradiction is a compound proposition that is false for all possible truth values of its component propositions. A tautology is a compound proposition that is true for all possible truth values of its component propositions. So it's the opposite of the contradiction. And a contingency is a compound proposition that is neither a tautology nor a contradiction. Logical equivalence. So logical equivalence, we have that symbol, 3 lines. Given any compound propositions, P and Q, P is said to be logically equivalent to Q. If the biconditional PQ is a tautology, it is denoted by this. Let's take a look at this example. If you notice, we have here the biconditional P then Q. We also have another here, not P or Q, and here the not, if not Q, then not P. They are 3 different compound propositions, but their truth value are identical. True, false, true, 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 false, true, 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 false, true, true. Then we could say that these 3 are logically equivalent. Predicates and quantifiers. A predicate is a sentence containing variables. Its truth value depends on the values to be assigned on the variables indicated. X is a real number, so we don't know if this is true or false unless we know the value of X. Y plus 2 is equal to 10. X minus Y is greater than Z. A predicate is also known as a propositional function, usually denoted by P of X, Q x y, R x y z, etc. A counterexample is a value assigned to a variable for which the statement is false. Once a value is assigned to variables, the predicate becomes a proposition with its corresponding truth value. However, there is another method to transform predicates to propositions. This is where quantifiers are introduced. Quantifiers refers to the amount to which a predicate is true over a particular domain of discourse, or simply the domain, which is a set of values for which the statement is defined. So you have types of quantifiers. Universal quantifier, denoted by this symbol, refers to the phrase for all, or for every, or for each. Example, for all values of x, element of real numbers, x squared is greater than or equal to 0. For all values of x element of natural numbers, x minus 5 is greater than 0. For all values of x and for all values of y, element of a real number, x plus y is equal to y plus x. Let's try to find the truth value of these statements. For all values of x, element of r, x squared is greater than 0. If we could find a counterexample, or one value that would make the statement false, then the whole statement becomes false. But since I think we cannot find, so I could say that this is a true statement. Next, for all values of x element of natural numbers, counting numbers 1, 2, 3, 4, 5, 6, 7, 8, x minus 5 is greater than 0. And this one is false. Okay, so to back up our answer that it is false, we need a counterexample. So I think if your x is equal to 1, maybe. Okay, so that would give me 1 minus 5 greater than 0, and that is negative 4 greater than 0, which is a false statement. Okay, so that would mean the whole statement is false. Next, on the third one is true. Next, we have the existential quantifier denoted by this symbol. Refers to the phrase there exists, or for at least one, or for some. For example, there exists x, element of real number, such that x squared minus 10 greater than or equal to 0. There exists an x, element of natural numbers, x minus 5 is less than 0. And the third one, there exists an x, element of integers, such that 3x plus 2 is equal to 6. Let's try to find their truth value. There exists an x element of real numbers, such that x squared minus 10 is greater than or equal to 0. If we can find at least one value of x, let's say for example, if x is equal to 4, so that would give me 4 squared minus 10 greater than equal to 0. So 16 minus 10 greater than equal to 0. That is 6 greater than equal to 0. So this is true. So I was able to find one, at least one. So that would mean the whole statement is true. Next, there exists an element of natural numbers, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, that would give x minus 5 less than 0. So let's say if your x is also 4, so that would be 4 minus 5 less than 0. That's negative 1. 0, which is true. Then again, I was able to find one value element of natural numbers that would make the statement true. So this is a true statement. How about the third one? There exists now an integer that 3x plus 2 is equal to 6. Okay, so if we try to find that value that would make this statement true, I will try to solve this equation. 3x plus 2 equals 6. 3x equals 6 minus 2. 3x is equal to 4. Divide both sides by 3. So x is equal to 4/3. And this one is an element of Q. rational. A rational number 4/3 is the only number that would make the statement true. So that would mean I cannot find an integer that would satisfy this equation. So this is a false statement. And that's the end of chapter 2.